lesson, we're going to focus our energy on introducing functions. Not only that, we are also going to determine not only what is and is not a function, but we also are going to talk about the domain and range of functions. And this is not just important here in college algebra, it's going to be important when you move to pre-calc, calc, and much further beyond. Domain and range are critical for some definitions. So let's first define what is a function. A function is a relation in which each x coordinate is matched with only one y coordinate. And if so, it's said to describe y as a function of x. So if we look at our two examples here, let's say our inputs are the x values on the left and our outputs are the y values on the right-hand side. We're looking to determine whether each x coordinate is contained with only one y coordinate. So each x coordinate goes to exactly one y value. So this is a function. Let's do the same with the example here on the right side. So 1 goes to P, however 2 goes to both P and Q. So because 2 is going to two different y values, we can stop here because this is not a function. Which of the following relations describes y as a function of x? This time I graphed my values. So I've got the graph of r sub 1 on the left and then the graph of r sub 2 on the right. Notice my points 1 here. Our x value 1 goes to both 3 and goes to 4. The graph on the left is not a function. However, when I look at the right, there are no stacked vertically points. It's okay to have them stacked horizontally because the value of 1 goes to 3 and the value of 2 goes to 3. So each x value goes to a different y value. So the graph on the right is in fact a function. Another way to determine this, if we're looking at their graph, is the vertical line test. The vertical line test is a set of points in a plane that represents y as a function of x if and only if no two points lay on the same vertical line. So in our example here, I can put a vertical line anywhere on this, what I assume is a quadratic, and it's only crossing my graph one time. There's only one point of intersection in each location. Thus, this is a function because no two points are stacked vertically on top of each other. However, the sideways parabola, it doesn't matter where I put my vertical line. Notice it's going to cross our graph in more than one location. Because of this, our points are stacked, and this particular value is going from the x value of 2, both a positive and a negative version, so not a function. Let's use the relations below. Do they describe y as a function of x? So if I'm using my vertical line test here, I see that a circle is not a function because it doesn't matter where I put my vertical line. It's crossing that circle in more than one location. Not a function. However, this particular one, no matter where I put my vertical line, it only crosses that graph one time. So this one is a function. Which leads us to want to discuss domain and range. So suppose f is a relation which describes y as a function of x. We can say that the x coordinates of the points in our function are the domain, and the domain works going left to right on our axes. And the set of y coordinates are the points in the function called the range. And the range we think about when we're talking about order goes from bottom to top. So in our particular graph that we have, notice we have a solid point here. So this solid point means that it's included. So when I'm thinking about going left to right, my graph is starting at this point, which is included, and it's going all the way until it's hitting what I assume is this vertical asymptote. So it's not going much past that blue line there, because if we notice this arrow looks like it's going to get closer and closer and closer, but not exactly touch it. So our domain, if I'm thinking about the x coordinates, my x coordinates are going from -5 included until we hit 5 here, which is excluded because it is infinity. It's there, but we're not actually going to touch 5 because it's going to get closer and closer and closer. It looks like a vertical asymptote. So our domain goes from -5 included all the way till +5, but excluded because it's not actually going to touch it. Now when I think about my range, notice I'm going forever to infinity. So my range, I'm going to think about going from the least value to the top right, so bottom to the top. So I'm coming from, in my range, I'm coming from -infinity, because this is going to go down forever and ever and ever. And the highest point I'm going to reach on my graph is that included point here at +5. So I'm going to come from -infinity, I'm coming all the way up, and I have to stop up here. Right? That's my highest point. So when I'm thinking about my y-axis, my graph is going this way. So I'm going from -infinity, the smallest value, all the way to +infinity, and because that was a solid point here, that means it is included. But what if I'm just given a set of points for my function? Find the domain and the range of the following. If I'm only given 4 points, my domain then is going to be all of my x values. And I'm just going to list my x values, and I'm going to put them in order from least to greatest. -3, 0, 4. Sorry, I didn't mean to move that. Fingers are just getting in the way. 4 and 5. So all of my x values. It's just a set of 4 points. My range is my set of y values, and I'm just given 4 y values. I'm going to put them in order. Notice that 2 is listed twice. I just need to 3 times. So I just need to list it 1 time. I don't need to write it all of them because it's just repeated. So my range is 1, 2. Here's another picture, another graph where we have to identify the domain and the range. So our domain, again, is the set of x values. So if I look here, this graph is not only going down forever, but it's also going to be going down into the left forever. So when I'm thinking about my domain, I'm coming from the left and I'm coming all the way until I hit this point here. But notice it's an open circle, so it's going to be not included. So I'm going to go all the way for my domain. I'm coming all the way from -infinity until I reach the point 1, and 1 is not included. That's the furthest right on my x-axis that we go, but it's not included. However, my range is a little different, right? Because I'm coming and I'm going down forever and ever. I'm going to be coming up from -infinity, so least to greatest, and the highest point I reach here is 4. And this is a point up here, right? Because that's a point 0,4 on the graph is this point. That is a point on the graph itself. So I have to include that. So my range comes from -infinity, its smallest value, all the way until I hit 4 on the y-axis exactly, and then I stop, and it's included because that is a point on the graph, whereas we had the open circle in the range. So some facts that are pretty heavily come up often. So all functions are relations because a relation is just a set of ordered pairs. So all functions are just a set of ordered pairs, but not all sets of ordered pairs are functions, just as we noticed here. So not all relations, not all sets of ordered pairs can be functions because they have vertical points that are stacked. Thus, equations which describe the relations may or may not describe y as a function of x. The algebraic representation of functions is possibly the most important way to view them. So we need to process algebraically for determining whether or not an equation of a relation actually represents a function. So how do we do this if I'm given just a bunch of equations? How do I determine if these equations are in fact just a relation or a function? So in order to do that, you can certainly graph, which we will do next. I'll show you how to graph them. Or we'll first figure them out algebraically and then visually verify that. So our first step is to solve the equation for y. So to do that, I'm going to subtract x cubed from both sides. Thus, I will have y squared equals negative x cubed plus 1. Then I will take the square root of both sides to get y by itself. So y is equal to the positive and the negative version of negative x cubed plus 1. Now I'm going to substitute 0 in. And we'll see this happen. I'm going to do this for every single item. Why am I substituting 0 instead of any other value? Well, 0 is easy to solve for, right? So I'm going to substitute 0 and see how many solutions I get. If I do this, I will have y is equal to plus or minus the square root. Well, negative 0 cubed is still negative 0 cubed, or 0 plus 1. Well, 0 plus 1 is still going to be 1. So I'll have plus or minus 1 when I take the square root of it. This tells me that 0 goes to positive 1 when I substitute in, and 0 goes to negative 1. Well, this means that it's not a function, right? Because 0 cannot go to two separate locations. Each x value needs to have only one y value paired with it. Thus, this is not a function. Let's see this in graph form. So I'm just going to grab Desmos here and substitute into Desmos. X cubed plus y squared equals 1. And we can see that, first of all, we have our two values here. We have 0, 1, and negative 1 that we had substituted in. But we can see that there's going to be lots of places, if we drew that vertical line test, that it would cross the graph in more than one location. So a way we can visually see that as well. Let's try another one here. We have x squared plus x cubed is 1. Again, I'm going to solve for y. Y cubed then is going to be the, negative x squared. So we have x squared and y cubed. So I flopped the square and the cube. Now to undo the cube, we'll take the cube root. The cube root doesn't give us a plus or a negative, so it's going to simply be the cube root of negative x squared plus 1. Still going to substitute just like I did before. And I'm going to use 0 again, since 0 is nice and easy to substitute in. Thus, y is equal to the cube root of negative 0 squared plus 1. Well, 0 squared is still 0 times negative 1 is still 0 plus 1. So the cube root of 1 is 1. we only have one solution for 0. So this one is in fact a function because 0 only goes to one value. So let's see what that looks like in Desmos. So I'm going to flip-flop here. I need to change this to a square. And I need to change this one to a cubed. Notice we've got our example of 0, 1. We only had one solution when we substituted 0 in. And I can look across and see that every single value when I use the vertical line test gives me one solution. I've got x squared times y equals 1 minus 3y. Well, if I need to get y by itself, let's just move to another screen here just so we have some more room. We've got, so this was example 3 on this one, so we've got x squared y equals 1 minus 3y. I need to get all my y's together if I need to solve for y. So I'm going to add 3y to both sides to get my y's together. I notice now that they both have a y, so I'm going to factor. I'm going to factor y, thus I'll have x squared plus 3 equals 1. Now I can divide both sides by x squared plus 3. Thus y is equal to 1 over x squared plus 3. Still going to substitute 0. And see what happens. Y then will equal 1 over 0 squared plus 3. So y is equal to 1/3. I have one single point that it provided me. So this is a function. And let's see what it looks like in graph form. So I have x squared y equal to, and I need to get rid of some items here, backtrack, backtrack. It's kind of fun to see the graphs change as we put new values in. Here's that 0, 1/3 that we found, but again, anywhere, if I put my vertical pencil on there, anywhere on this graph, we have a vertical line test that passes because it crosses our graph one and only time. And that concludes our lesson on the definition of functions, as well as an introduction to domain and range.